Hey y'all, Coach Spots here. We're just going to talk briefly about graphing exponential functions. So today's content is going to be all about graphing exponential functions. So they actually start with this basic format for all exponential functions. Our function of x is some numeric value, potentially, doesn't always have to be an a value there, times some base value raised to the x minus h power, doesn't have to be another constant there, h, plus k. Now, numerically, there does not have to be an a value, there does not have to be an h or a k, right? We could just have something like this. F of x equals some number raised to the x power. The whole concept here is what makes this an exponential function is that our variable is now in the exponent, okay? So all of our exponential functions have the variable in the exponent. And this is a basic, simple example of that, where if we were to make a t-chart of x and y, we could start with x equals 0, and we just do 3 to the 0th power. Okay, so 3 to the 0th is 1. We could find x equals 1, so 3 to the 1st is 3. Oops. I don't know why I just did that. 3 to the 1st is 3. I can find x equals 2. 3 squared would be 9. 3 to the 3rd would be 27, and so on and so forth. And you see your outputs are growing exponentially, right? So kind of keep that in mind. And you see the pattern that's happening. You're multiplying by 3, okay, each time. Because every time you increase your exponent, that's another multiplication of 3. Just like if you were to decrease your exponent, going from an exponent of 3 to 2, you are dividing by 3. And every time you go backwards, you're technically dividing by 3. So I guess one of the things that means, let me clean this up. One of the things that means is if we went so far backwards that we went to like a negative exponent, -1, that means we would have had to divide this 1 by 3 to get that. And we would have had the x value of, or the y value of 1/3, which makes sense because if you recall, 3 to the -1st is the same thing as 1 over 3 to the 1st. So we did that topic already. And obviously this is just an example. But if you plot this example on a graph, okay, we have the coordinate 0, 1, 1 comma 3, 2 comma 9, so it's starting to grow pretty steep. Okay, over here, -1 comma 1/3. If we went to our -2, that would be -1/9. Sorry, that would be +1/9. I don't know what I'm doing there. Okay, so I'd have boom 1/9, and it would get closer and closer to basically the flat line of 0. Now, the way I introduced this in class last week or a couple days ago was that there's this kind of imaginary flat line that's not a part of our graph that we're actually calling, it's called an asymptote, right? And it's not a part of our function, right? Our function itself is just this curved exponential, and hopefully I can do a better job showing that this curved exponential never actually reaches this flat line. It's going to always, in this direction on the left, it's going to always approach this flat line, but never reach it, right? It's just going to keep getting closer and closer. Even if it's a minuscule distance away, you can think of it as long as there's some starting distance away, we can remove some of that distance, get closer, and still leave some distance between our curve and the line. So it kind of flattens out to that asymptote, okay? This is the basic idea. Clearly this is a growth function because over time it shoots up exponentially far, okay? And it is growing. So that's just an introductory example, okay? And obviously you see I created a little t-chart in regards to how to find that, okay? So today, we're going to look at these types of functions. Now, to give you just a quick summary, we could have a number here. It could even be a negative. There could be a number, there must be a number as its base. Right? It could even be a fraction. It must be raised to a variable. Okay? And sometimes there could be something added to that x value, or that variable within our exponent. And there could be something subtracted or added on the outside as well. This is just an example of what we could have in an exponential function, all right? The only thing that we must know is that our base is never allowed to be negative. We can have a negative out here, but our base is not going to be negative, and it's also not going to be 1, okay? Or 0, because otherwise it doesn't take that shape, okay? And in fact, this value right here is actually going to be used in identifying the asymptote. So that value is actually, whoa, something's up on my screen, is actually going to be the height of the asymptote. If you want to write that down right now, that's probably a great thing to have in your notes, okay? That value k is going to be the height of the asymptote. So in our initial example, if you recall, we had, and if you just look at our initial example, we had 3 to the xth power. We had nothing on the outside, right? There was no plus k. Well, in reality there was, it was just plus 0, okay? But we don't need to write plus 0. What that told us was, hey, 0 is the height of the asymptote. And if you recall the line that we just had, if you rewind this video and see the graph that I had created, remember? The graph that I created looked kind of like this. And we even showed a height of 0 as our asymptote, okay? And if you notice our asymptote, it is a horizontal line, which means we write equations for our asymptote like a horizontal line. We'll get to that later. I just wanted to kind of preview everything right here. All right, so let's go level 1 type of question that we're going to ask you. So we're not even going to get into graphing today. We'll say that for tomorrow's lesson. But we'll say level 1 type of question we could ask is we could just give you a basic exponential function and ask you if it's growth, decay, or neither. And that's what you're going to see on your homework a lot tonight. So y equals b dx. So something simple like y equals 2 to the x. And basically, here's what we're going to do. All we're going to look at is our base value. I already told you our base must be positive, and it's not going to be 0 or 1. Okay, so basically, if our base is between 0 and 1, we would call it decay. So we cross this off so you don't confuse that with this problem. If the base is between 0 and 1, it's a decay function. If our base is bigger than 1, it's a growth. Basically, if you raise something to an exponent and it's bigger than 1, it's going to keep getting bigger and bigger and bigger. And if it's less than 1, it's going to get smaller and smaller and smaller. Okay? So let's talk that through, as long as it's not negative, right? You guys are used to seeing the following, because we've already dealt with some exponentials. You guys are used to seeing growth problems that look like this, right? Some initial value times 1.03 to the t power, if we had y of t. So just kind of reviewing what we've already done. Okay, so forget this over here. Reviewing what we've already done, this is like, hey, there's a population that started out with 10,000 people and it's growing by 3% each year. Clearly a growth because guess what? This is above 1.0. Okay? And then we dealt with stuff like this. Okay? Hey, your car that you bought, it was worth $10,000 originally, but it's only retaining 73% of its value each year. It's losing 27% value each year. It's decreasing in value or depreciating. We know that this would be a decay problem. So these are examples that we have already gone through this week. Okay? So building off that knowledge, What if this was not there? Well, that's okay, it wouldn't change the problem. What you're looking at is the base every single time to determine if it is growth, decay, or neither. So now let's get back to how these functions would look. Function of x is some number 2 raised to the x power. What you would do is you would look at the number 2, okay, because 2 is bigger than 1. This would be a growth problem. Boom. Okay, so that's our first example. Hopefully you're writing this stuff down. All right? All right, let's do another one. F of x equals 1/3 raised to the x power. Okay? Once again, we just look at our base. Our base is a fraction. Now, not all fractions are less than 1, but this fraction is less than 1. So it is decay. All right? And that's basically how we're eyeing this. Okay? So, let's go again. 5 to the x. Tell me what you think it is. Write it down. Growth. Good. Okay? Again, you're pausing this video, hopefully, or writing it down as we go. Okay? Let's try another one. 3/4 raised to the x power. Actually, I forget. I'm just going to be pressing play in class tomorrow for the students that are face-to-face. So let me give you guys a minute to actually write this down and then take notes on it. Identify if you think that this is growth, decay, or neither at this time. Yeah, I'd say decay. How come? Because 3/4 is less than 1. All right? Let's try another fraction. Let's go with f of x equals 7/6 to the x power. Growth, decay, or neither. I haven't even gone over neither yet, so it probably isn't one of those. Okay? It's either growth or decay. Well, this is a fraction, but 7/6 is bigger than 1. Okay? 7/6 is bigger than 1, so this is growth. All right? Now I want to make this clear. For each of these problems, when we have some b value raised to the x power, okay? Like for example, we'll go with 4 to the x power. If you add in something out here, like 3, and you add in, first off, 4 to the x power, that's a growth problem. You guys with me on that? Yes? All right, good. What I'm saying is if you add something outside of this, that does not change that it is a growth. All that does is change the height of the asymptote. Okay? That's all that does. It does not change that it's growth. It doesn't affect our base whatsoever, right? Our base is still right there. It has no effect on our base whatsoever, all right? And in fact, if I add something up here as well in this exponent, like the whole exponent is x plus 1. So imagine the entire exponent is x plus 1. That does not impact our function whatsoever, as far as if it's growth or decay. What this does is this changes the location of the y-intercept. Okay, that's all this does, is it helps to change the location of the y-intercept. All right? And it doesn't matter if these had been negatives, like if this was a -1 or a -3 on the outside, that still does not change it whatsoever. Look at this, there's no one in school, and I'm going to deal with these bells interrupting me. Okay, so this still does not change it. The only way that this would change to a decay function is if our base itself changed to a fraction that was less than 1. Well, I won't say this. That's not the only way it would change to decay, but we're going to get to that on like level 3. But if I changed the base to make it something less than 1, now all of a sudden this would change to decay. All right? So, correct me if I'm wrong. Do you guys all agree that this is a decay function? Yes? Okay, let me give you the basic viewpoints of what decay functions look like. Decay functions, and I'll just draw a basic asymptote at 0. They have an asymptote, okay? And the function decays into that asymptote over time, meaning over time, maybe that's not the most beautiful curve, maybe it could even be steeper into that. Over time, our function decays into the asymptote, meaning as we go further in the direction of time, right, to the right, what that means is our function's height dissipates into no distance away from our asymptote. It gets really, really close to touching it. It never touches it, but it gets close to it. Now, let me make this clear. The function could have different heights, right? The asymptote could be raised, right? The asymptote could be down there, but the shape of a decay function is always this same model where it is above our asymptote. In order for it to be a decay function, it's above our asymptote and it decays into the asymptote over time. As opposed to, for a growth problem, you can think of it as it grows away from our asymptote over time, meaning the side that approaches the asymptote is on the left, and then it grows away from it over time. Once again, though, and this could be at any height, but what has to happen is it is literally growing away from the asymptote, where if we go infinitely far to the left, it is, so to say, getting closer and closer to this asymptote. So it started really, really close to the asymptote, and then it grows away eventually at a point where it's just growing really steeply and quickly because it's exponentially growing away from our asymptote. And again, it could be at many different heights. Okay? Oops, sorry, like this. Boom, many different heights. The key, though, is that our function, our graph, is above the asymptote. Okay? In order for it to be growth or decay, it is above the asymptote. Now, we talked about what would make it a neither function. Okay, here you go. If you have a negative in front of our base, what that does is it takes every value and it flips it over our asymptote. Meaning, so here was our original function, and it was a decay function, 1/2 to the x. So 1/2 to the x looks like this. I just know that off the top of my head, but this is clearly a decay function by shape. Okay? What it's saying is it flips it over this asymptote. Such that it's a perfect mirror. So if this top scenario, is 1/2 to the x, this bottom scenario is the negative of 1/2 to the x, where every idea has been flipped below the asymptote. All right? And this type of problem is neither growth nor decay. We don't call it true growth or true decay. I realize that it is decaying into the asymptote over time, but it's actually increasing into that decay distance. So it's got like a negative decay to it. So we don't even call it that. We call this neither growth or neither true decay. Okay? And we attain that strictly by having a negative in front of our base. So what would have been decay is now a neither function. Okay? And that works the same with what could have originally been a growth function. For example, if we had 2 to the xth power, clearly a growth function, and we throw a negative out front. Let me make this clear. This negative that's out front is not inside parentheses. That is not it, because we said the rule, the base does not have that. It is actually treated as if the 2 is raised to the power separately, then we apply the negative afterwards, as if it was outside of parentheses. Okay, but we don't really ever draw those parentheses there. We just leave it like this. And when that's the case, this negative right here makes this a neither function. Okay, so let's look at those two functions, right? Here would be our asymptote. Here is 2 to the xth power, be above it. Notice this is growth. And then if we had negative of 2 to the xth, that would look like that. It's like the mirror. And we would call this neither growth nor decay. All right? So that's level 1 difficulty, and that is completely not affected by anything out there or there. All we're looking at is this or this to determine if it's growth, decay, or neither. All right? So this is examples of what would have been a growth function. The negative just flips it. So basically, if the picture is below our asymptote, if our function's curve is below our asymptote, then we would not call it growth or decay. We would call it neither. Same thing here. What was previously a decay problem is now a neither problem when we put the negativity there. Okay, level 2. Now we have a numeric multiplier out front. Check this out. So let's say we have 3 times 2 to the x. Check this out. Once again, we're only looking at this base to determine if it's growth, decay, or neither. We don't even care about this in determining if it's growth, decay, or neither. We literally just look at that 2 and we realize, hey, this is growth. Okay? And it doesn't matter if there's something attached there or there. All right? It has no impact on if it's growth or decay. Right? And it doesn't matter if that's a fraction out front or a whole number. It is still, we are only looking at the base. Well, that's not the only thing we're looking at, but if this is positive out front and there's a base here raised to a positive x power, we're just looking at the base. Let me clarify because level 3 gets a one notch more difficult. Okay? So let's try this again. So let's look at, let's go with y equals 5 times 3 to the x minus 1 plus 2 power. And we want to identify if it's growth, decay, or neither. So check this out. Things that don't matter. The 5 doesn't matter. The plus 2 doesn't matter. The minus 1 doesn't matter. The only thing that matters is it's got a base of 3 raised to a positive x power, and there's a positive out front there. This is a growth problem. Okay, it's just 3 raised to an exponent for all intents and purposes. Okay, let's change this to be 1/4. Once again, it doesn't matter about this number, it doesn't matter about this number, and it doesn't matter that this number 5 is bigger than 1/4. Okay, it does not get to distribute into that. That is not allowed because it's raised to an x power, this idea. Or it's raised to an exponent, that idea. So we cannot just use the distributive property. We are literally looking at 1/4 isolated from everything else, which is why it's a decay problem. Okay? Again, it doesn't matter that we have this other stuff there. For all intents and purposes, it's just 1/4 raised to the x. This changes the steepness of it, not steepness, the curvature, how quickly that curvature shape happens, but it doesn't change, right? This changes like if it's stretched or shrinked. It doesn't change the actual rate at which it's exponentially growing or decaying, okay? So let's now throw one more trick at us. If we put a negative out front, that does impact this problem now. Now we have a neither function, okay? So now it is neither. It doesn't matter if we have something there or here, okay? And it doesn't matter if we have this there or not. In fact, the last problem we did, right, we were showing, oh, do you want to say it changes? Oh, cancel that. I don't want to close this out. Right. The last problem we did over here, we had the negative, it was just a negative out front. You can think of that as like a -1 out front, right? Or if it's a -3, all the more reason for it to be a neither function. And this doesn't have to be there, this doesn't have to be there whatsoever. And even if this was a original growth problem, like it's got a base that would typically lead to be a growth problem, this gets trumped by the fact that our function has a negative out front, meaning it is below, and it would actually be this one more than likely, it is below our asymptote, okay? So that's level 2. Level 3, when we have a negative exponent for our x, okay, or a negative coefficient for our x, which is an exponent. So here's what I mean. 3 to the negative x power, okay? When we have a negative exponent that is our variable, it is as if this problem has been flipped and this base is now the reciprocal base. You with me on that? So this function actually becomes this function. That's what the negative exponent does, which makes this a decay problem. Okay? Now, if you have something there, it doesn't change it. It just makes this a little bit more difficult because you have to factor out the negative here too. So we really are going to disregard that scenario from a complexity standpoint for you guys, as far as understanding what you need to understand. What you need to know is, let me phrase it the right way. What you need to know is, hey, this normally would be a growth problem, but the x is negative, so therefore it's a decay, okay? And if you had numeric value there, that's fine, it doesn't change the fact that it's decay. And if this was a negative, it doesn't matter, it's still decay. What matters is, was a growth, but now it's to a negative x, so it's a decay, all right? Where it gets really fun is when we throw a negative out here. Now all of a sudden it doesn't matter that it was growth, became decay, because now it's got a negative. So boom, oh, that's not what I grabbed. So boom, now it's a neither function, okay? So let's go to another one. 1/2 to the negative x. Check this problem out. This was decay, but it's raised to a negative exponent, so now it's growth. And it doesn't matter what number we have out front, as long as it's not a negative, which would then make it, which would then make it a neither problem, okay? And if we add something out here or up here, that still does not change anything. But if we took this negative away out there and left this negative there for the x, right, this is a growth problem now because it was decay based on the base raised to a negative exponent, so now it's growth, all right? So that's kind of everything as far as identifying if something is growth, decay, or neither. Hold on. All right, the next skill that we're going to be getting into is writing the equation of our asymptote. Now, if you recall, our exponential functions were y equals a times b to the x minus h plus k. I know, a lot of complicated stuff. Basically, it's all numbers except for the x. Right there. And we said earlier this plus k, that is the height of the asymptote. We also said earlier Asymptotes are just horizontal lines. So recall, how do we write the equation of a horizontal line? Y equals some number, some constant, in this case k. So that's actually how we're going to write the equation of the asymptote. So if I had my function is 3 to the x plus 2, the first thing we would graph would be the height of our asymptote, which we're identifying as plus 2. So that would be our asymptote. Okay, that's the picture of our asymptote. We get that from this plus 2 right here, which means our equation for this asymptote is, it's a horizontal line, so y equals the height of 2. Okay? That's literally all this is. Basically, if we were to lower this, and this was in -1, all that would do is lower our asymptote right there to the height of -1, which changes our equation of our asymptote to be y equals -1. Must write y equals because it is a line, it is an equation for the line, and it is a constant height, right? The y variable is our height variable. The height is always constant at the height of -1. Hey, that sounds like a pretty much horizontal line, okay? I heard someone say the other day, like a flat line. I was like, oh, hey, that's straight. And then someone was like, oh, it's a straight line. And I was like, well, I'm pretty sure most lines are straight. But we can say it's a flat line. It's got a constant height of -1. Let me make this clear. If we add something up top, that does not change the asymptote whatsoever. If we change our base, that does not change our asymptote whatsoever. If we put a negative out front, that does not change it. If we put a number out front, that does not change it. If we make that a negative, that does not change it. The only thing that matters in finding this asymptote is this number right there that is added or subtracted at the end. Okay? So let's practice that again. F of x equals, and I'll put the whole kit and caboodle here. That's like a phrase, by the way, for those of you youngsters that don't know that. To the 2/3, sorry, -2 times 2/3 to the negative x plus 1 power plus 4. Let me make this clear. I'm not asking you to graph this yet. This is above your pay grade as of today. But we will eventually get to where this is pretty easy. And that's why I'm teaching you step by step the ways to think about this. And today, the only step I'm asking you really to know is, hey, that's plus 4. Okay, so that means our height of our asymptote is at 4, right? And that means our equation for our asymptote is y equals 4. All right? And what about if we've got a bunch of scary stuff here, like 2 times 1/3 to the x plus 3 power, and we wanted to know our asymptote? Okay, well, first, we would just look at what is this number over here. Well, there's nothing there. There's no extra number there. It's like a 0. Well, guess what? That's allowed. We're allowed to have nothing out there. Our asymptote would just be at y equals 0. That height, flat right on the, what's the word I'm thinking of? The x-axis, okay? And if we got rid of this and got rid of this, it's the same thing, okay? So now, let's talk about domain from one of these functions. Okay, so let's give you a function, f of x equals 3 times 1/2 to the x power plus 5. Guess what? It doesn't matter what function we have. If it's an exponential function, our domain is always all real numbers, and this is how we write that using interval notation. Let me say that again. Our domain is all real numbers for all of these exponential functions, and so this is our interval notation way of writing it, from -infinity to infinity. Okay, so let's talk about range then. Let's say, all right, Coach Spots, domain is pretty easy. I got that. I got no problems there. Let's talk about range. Well, range is going to differ. And range talks about the heights that we want. So guess what concept now comes into play? That's right, the asymptote. That's the only thing that we really matter right now, is identify our asymptote, plus 5. Once we identify our asymptote, guess what? We have only a couple options. Our function's above it, or our function's below it. Right? Do you guys agree with that? That's literally all our options, right? And if we list out our important numbers in life, 5 is right there, that's that height. Way down at the bottom is negative infinity, and way up at the top of the world is positive infinity, right? So I've got, these are basically the 3 numbers that I care about now for our interval notation of range. Start at the bottom, negative infinity, and goes to 5. That's one option. Or starts at 5 and goes up to infinity. That's the second option, right? My function can literally either be above it, and this is decay, above it, and it's growth, or below it as one of my 2 neithers, right? That's pretty smart thinking. So we know where our asymptote is, and now we just have to identify what type of function is this. Well, this has 1/2 is my base. It's got a positive x there. And again, it doesn't matter if we had a negative number attached to the x. What we care about is that it's a positive right there in front of the x. So we've got 1/2 is our base. Make that a little cleaner. There we go. 1/2 is our base. X is our exponent. It's positive. So we've got a decay base. Nothing changes there. Nothing flips. And we've got no negatives there. So this is a decay problem. Boom. We know because there is no negative in front, we know, hey, there's no negative in front. Therefore, we know that this function takes place above our asymptote. And that means that our function is going from 5 to infinity. Y'all with me on that? And again, it never touches 5, because we already said it never touches our asymptote, and it never touches infinity, because no one can touch infinity. So our range would go from 5, whoop, that's an ugly infinity sign, let's draw a pretty one. Dang, that's a pretty infinity sign. All right, there's a lot that I covered there. So let's do another one. F of x equals, okay. Hey, this is a long class period. I don't have much time left. Okay. F of x equals -5 times 3 to the x plus 1 minus 1. Okay. We want to find our range. Copy this down. F of x equals -5 times 3 to the x plus 1 minus 1. First thing we want to find is our asymptote. It's at the height of -1. So here it is. Whoa, that's ugly. Oh, that's beautiful. Okay, there we go. So we've got y equals 1 would be our equation of our asymptote. Remember, infinity is all the way up here. Negative infinity is all the way down here. We're looking at one of these 2 intervals. Either our function goes from 1 to infinity or negative infinity to 1. That's our 2 options, right? Think about that. It's either above the asymptote or it's below the asymptote. That's all we have. It's the only possible options. So let's look again. 3, that's a growth. Positive x. Okay, nothing's changed. It's still a growth. Oh, there's a negative out front. So this is a scenario where it is below our asymptote. And I'm not asking you to quickly be able to draw that curve, but this is what a negative growth would look like, etc. Okay? It doesn't really matter. All that you need to know is that this is the interval of values for our range. Negative infinity to this -1. By the way, that should be a -1. Can't believe I left that out there for so long. Shame on you guys in this empty audience not correcting me. Okay. Interval, negative infinity to -1. So there's a couple examples right there on range. And I know that Delta Math will do a great job also explaining this. And thankfully this YouTube video is going to be posted, so you guys can watch this again later tonight when you're doing your homework if you want to. What I want to get into now is the final skill, which is identifying our y-intercept. Please keep in mind, y-intercepts are points. It is a coordinate. Which coordinate is it? It is the specific coordinate where it touches or crosses the y-axis. Well, if it crosses the y-axis, it has an x value of 0. Okay? So, the key theme, for every y-intercept, we have the x-coordinate of 0. We're not even going to ask you to graph it and count. We've already done that for homework. This is a scenario where, where we give you the function and all we're asking you to do is substitute 0 in for x. That's literally all you're required to do. So we've got 2 to the 0 plus 1th power. Again, it's not always going to be the 0th power. It's going to be 0 for x, meaning the 0 plus or minus some other number power. Okay? So this becomes 2 to the 1st power plus 3, because 0 plus 1 is 1, which becomes just regular 2 plus 3, which is 5. Check. Y-intercept is 0, 5. Y'all go with that? Running short on time. It's okay, this video is going to take up the entire class time tomorrow. Which stinks for me, because that means I got to listen to myself talk and teach 3 classes in a row. So, good news for you guys, you only have to watch this once. I had to create it, think about it, prep it, do it. And then tomorrow I'm going to have to watch it 3 more times. I'm going to walk home tomorrow. Not walk home, I drive home. I'm not. Anyways, I'm going to leave school tomorrow fully annoyed by listening to myself. So I very much understand where all of you kiddos are at. So sorry. I know you guys got to deal with teachers all the time. Okay, so negative 3 times 1/3 to the x power plus 2. Okay, copy that down. And again, now we are substituting this 0 just to right there. So we've got negative 3 times 1/3 to the 0th power plus 2. Well, what's nice, I don't know, fractions are not fun, but what's nice about the 0th power? That just becomes 1. Okay? Negative 3 times 1 is negative 3. Negative 3 plus 2 is negative 1. And that's our y-intercept. My computer's literally about to die. I haven't saved this yet. This is a 43-minute video, so I got to shut it off now, because if I lose this, I'm going to be very frustrated with myself, because I'll have just wasted 43 minutes of my life. But this was a baller lesson, so hopefully it's